Euler's formula. I started this course, the very beginning of this course, this was my propaganda statement. There is this basically two important transcendental functions, right? Exponential and trigonometry. And it was different function and completely rises in a different nature. And different number system, they all rise as the same principle. It's like a same function, right? So they all, like the one function in complex numbers, right? Turns out that. Looks like a different function, we define it a different way, but if you use complex numbers, these two different transcendental functions become the same function. Okay? Alright, so let's clarify that. This important earth-shattering formula, each of these, so far we have definition of this exponential for real numbers. So here we're defining I times the theta, where theta is a real number. So let me just write underneath it like this, clarifying. So I times the theta is a kind of purely imaginary number. There's no real part, right? We're giving a meaning to that, and you probably all know what this one is. So what is e to the I theta? Because you've seen it in the book a lot, right? What's e to the I theta? This symbol means we're defining. This one, by Euler, is defined to be this complex number. Cosine theta of that real number plus I times sine theta. Okay? So here's one thing I want you to distinguish in here. We already know what the right-hand side is. We've been using this a lot in a polar form, right? One thing you should not do is that do not look at this as shorthand notation of the right-hand side. That's not what this one is. What this one is we're extending the meaning of exponential function to this type of a number. And that's what this one is. Okay? That's our definition. It extends the real function into a complex function. Not that we've been using this a lot, and we're going to abbreviate this one like that. That's not what this one is. This one is extending this function. Okay? And there's this big question. There's this existing world, right? And we're extending it. Just like there's an existing real number, and we're extending it under the hypothesis that this number whose square is -1, right? And next question I ask is that, is this okay? Right? Is this going to be okay? Is it going to be collide and give some contradiction? Right? And we're going to definitely answer that question later. But if you do it like this, everything fit perfectly together, and we have this wonderful thing shows up. That's what this formula is about. It's Euler's suggestion. So let me say one thing and I'll let you go. So I said I want you to look at this as a function. As a function there. That's the important part. And that's some algebra formula or abbreviation. So I hope you understand the domain and range relation of a function, right? So if I have real functions such as f of x equals x squared, the domain, and we say it's a codomain. Domain is an x-axis, and codomain is a y-axis. Do you know that? And then we put them together, so show that domain and codomain relations. Like that, if I have one point in the domain and your codomain is put them together into a graph like that. But if we look at the complex functions, your domain is already one plane, right? Okay, think about that. So here, this is not domain and codomain put together. This is domain, right? You know the number table, when you introduce functions to the beginners, you have one column, you have list of numbers, and the second column you do the function and you write them down. That's the same thing I'm about to do in here. It's like a number table, but the table has lots of positions. Instead of, numbers listed, this whole thing is just that domain in there, right? So here's what is this guy here? Another, they usually put this UV plane. This is the codomain, right? Codomain. Like number table. So if you have each of the points, for example, if I choose I there, where does that go? That's all you have to understand. What is the function in here? Is it e to the z? That's the function I'm looking at in here. Z is a complex number, and this complex number happened to fit in exactly that way. So e to the I, the first one, looks like e to the I. Okay? This is your input, I, and if you plug it in there, z equals I, then this e to the I. Who knows the meaning of e to the I? That was exactly the Euler's formula. So it's e to the I times 1. Is that right? Looks like e to the I times 1. So what is e to the I times 1? According to Euler's formula, is a cosine of 1 radian plus I times sine of 1 radian. E to the I, according to Euler, is defined to be this complex number. What is the real part of the complex number? Cosine 1, right? What is the imaginary part of the complex number? Sine 1. Seems like it's difficult to sketch it without calculator, but this has a geometric meaning, right? This is a polar form. What does that mean? Modulus. What's the modulus of this number? 1. Invisible 1. What is the argument here? 1 radian, right? 1 radian is pretty close to 90 degree, or slightly less than 90 degree. Right there. That number right there, right, is radius 1 and angle 1 radian. You locate that complex number. So it's like a number table. If you choose that number I, where does it go? It goes there, right? Okay. What about half I? Where does that go? Exactly, it's going to be I over 2, right? So that's exactly half of the angle. So it's going to go to that half angle right there. If I look at that. Okay? Consider this one just like a number table. Here's just organize it in a different way, more geometrically. So what is each point is going? And this is one way to visualize what complex function is doing geometrically. Okay? We already done that for z to the n. Z to the n is if you have a number with rotating n times argument, things like that. Okay? So if you look at the next chapter, limits and continuity and all that is driven to understand function geometrically like that and analytically just like we do in the calculus. Okay? I'll stop here. So modulus 1 and argument 2 radian, where is it? I think it's somewhere over here, don't you think? Okay, that's d prime. All right, that was our test problem today, right? So hope this kind of helps you to see what this function is doing as a transformation. I have a bunch of points scattered apart like this, but you will see today a bunch of points are lined up nicely so you can see those beads of those points where they kind of lined up. That's what we're going to see. All right. Again, I'd like to emphasize that this is the efforts I'm doing and they're doing to view this Euler's formula as a function, not just an algebraic thing. All right, so let's continue. And also, the homework problem was, what was the homework problem? Was that e to the I theta, that's a complex number, we defined that, right? And then you raise that to nth power when n is a positive integer or negative integer. Okay, so if we just simplify it inside as a complex number and raising to a positive integer and negative integer, it makes perfect sense, right? If you just look at a complex number, not at an e to the I theta. Complex number raised to nth power. Makes perfect sense. And this was equal to e to the I n theta, right? That was what asked to prove. This is not automatic. This we just defined and extended this exponential function. So this exponential law you had it before, it is not automatically true. You have to show that this is true. How was that problem? Was that all right? Okay. If you look at the De Moivre's theorem in there and write it as a Euler's formula and use the De Moivre's theorem, you get to this spotting immediately. All right. So it's an important statement. All right, so this is, I'm saying this is a positive integers or negative integers. That's an important statement. Okay. What if I have e to the I theta of 1 over n? It's nth root, right? It's nth root, is that right? In the real number, how many nth roots do you usually expect? In the real numbers. If I give you a real number, negative 2014, I ask you to think about what's the third root of that. How many real roots do you expect? Nth root. 1 or 2. N is even, possibly 2, you think about it. And n is odd, there's only 1. Even, they simplified it. When we put something like this, it's going to be just square root and fourth root. We're going to choose by convention. We're going to choose positive roots, right? So we make these choices. If this base here is a real number, 1 over n is by convention, it's pointing to the positive roots, right? That's the convention. So if I write 2 raised to 1/2, usually we write square root of 2. Square root of 2 is the positive real root of that. Now, in the complex number, we know there are a lot of them, right? Always write a lot of them. And then the question is, which one by convention are we going to point this one? There's a way to do that. One that is in first quadrant with the smallest. There's a way to choose it, right? But there's nothing, not as convenient as a positive and negative. Looks quite artificial. So they decided to not define this one clearly. We just leave it like that. This is a little bit undefined. You will see they eventually does that, but there's something to think about in here, right? Not to mention the 1 over n, if you pass to real number, pass to complex number, you really have to think about what could be the definition of that. So that's why I'm tagging it carefully there in the problem. N is a positive integer, negative integer. Only this part makes sense to us right now, not raising to anything more complicated, right? Eventually, we're going to go to, I have a complex number z, I want it to raise to a complex number w, and we have to extend it to that, right? Okay, but right now this all makes sense because n is a positive integer, negative integer, and that's very algebraically easy to understand. But z to the w is very hard to understand algebraically what that could mean. But it's going to lead us to only one option for the z to the w, so it's well defined. All is coming from Euler's formula. So that's where this homework problem is heading. It's the important thing that there's sensitive things involved in there. So finally, our analytic continuation. E to the, we only define for I theta, the one that is the vertical y-axis, right? What about all the other complex numbers? That's what we're about to do. Okay, so the complex number looks like x plus yi. Is that right? We have to define this one where x and y are real numbers. Then the numerator, the exponent looks like, covering all the complex number x plus yi, right? If x is missing, we know what that means, correct? If x is missing, that's Euler's formula. If x is there as a real number, how should we define that? And is this a suggestion? Why don't we define it like this? I have cosine y, I times sine y. That's only the e to the yi part, right? And we want to accept it exponential law. If x is there as a sum, how does that correspond to as a, you know, correspond to as a product, right? So e to the x is there, seems like it's the way to go. So that it obeys exponential law just for that e to the x and e to the yi. So it's motivated by e to the x times e to the yi better be what? E to the x plus yi. This is happening for the real numbers. Why don't we use that natural idea to extend this one? Now this is fully continued, right? Any complex number you stick it in there, we have a meaning to that. Let's remember if you look at this component here, if you look at complex numbers in that shape, what is this x is contributing to? Is contributing to modulus of this whole complex number. Modulus. Modulus of what? What complex number? If you look at the right hand side, that's exactly the unit circle part, and that's exactly the modulus, is it not? E to the x is a positive number because it's a real exponent. So that x goes to contributing to directly to the modulus, right? Not involved anywhere in here. So the this x is contributing to modulus of this whole thing is better simply denoted by e to the z. If you're looking at e to the z, what is the modulus of this e to the z? That's coming from the real part of the input. Does that make sense? If you look at y part in here, you look at the z part, and you're staring at this imaginary part, how is that contributing to? That is contributing to the argument, right, of e to the z. That's not conjugate. Just, there's error there. Does that make sense? Okay, that's what that is. So let me sum up. This is the important statement. This is a full definition of e to the z. It's a definition, not a theorem or anything. If you look at the e to the z, you separate the real part and imaginary part, goes to modulus and argument like that. That's a definition, motivated by that theorem. So let me summarize it here like this. All right. Number one, important property. I am looking at this complex number where x and y are real numbers, right? If I put this absolute value, what does that mean? It means modulus of this complex number, right? What is the modulus of this complex number? E to the x. That make sense? Okay. One more thing that you might encounter. What is the modulus of e to the yi? You know that? 1, because e to the 0 is, you can insert it, and that's exactly 1. So when you stare at this complex number e to the z, you need to get used to how am I going to visualize this complex number. This is one way. That's the modulus this, and that's argument this, right? That's one. So how about this one? What is the principal argument of e to the x plus yi? Tricky question, right? Principal argument. E to the x is a modulus part, and what was the argument? What was an argument? So y, right? But principal argument has restriction, remember? Therefore, it has to be adjusted by integer multiple of 2 pi. So it has to be adjusted, 2k pi. So that the argument of e to the x plus yi is in what range? Pi to negative pi. That's convention because of the symmetry probably chose. There's nothing wrong with it 0 to 2 pi, but they chose this pi to negative pi, and so that's the convention. That makes sense? Helps you to visualize what on earth is e to the z is, right? So that's one thing. So this part is going to be homework, and I find this mathematical setup. So what I'm going to do is that I'm going to show you the domain plane and plot a bunch of points and see where that is taken under this e to the z function. We already did that for z being purely imaginary number. All right, so here is a set A I'm defining. So table of the value, for example, k plus 2i. So k going from -3 to +3. by 0.1. So you know what that means, right? Is I think it's too small, so I'm going to make it a bit bigger. Big enough? So we're going to collect these k plus 2i in the domain plane, right? And k is varying from -3 to +3, increased by 0.1. So there's like 60 some points somewhere there, right? All right, so that's that, and we know that's going to be. Then this is how you plot it. So how do you do that map of real part, right? An imaginary part from A. Then that's going to be list of points, imaginary part and real part collected like that, correct? So if I call that one as a fig of domain of list plot of that AXY, and that's going to plot it, right? That's going to plot that. And if you want to plot it later together, and you can use this fig domain command to do that. So this is a domain plane, right? This is a domain, and as you hit this one with the exponential function, where do they go? That's our question, right? All right. So I'm going to first continue, and I'm going to leave it there. How do you calculate this B, which is the image? Okay, it's a map. Each of the points is coming from where? A, right? This is a complex number. You take that complex number, and what do you do to that complex number from the domain, those 60 some points? We hit it with the function, right? What's the function? E to the z function. That's what we are trying to do. So how do you write e to the z? They already have all this complex definition in it, so you can conveniently write that here I have a complex number. I'm going to hit it with that. So take that all the complex number from A, from domain, selected points, and hit it with the exponential function. Mathematics already know how to handle exponent and exponential. All right, so if I do that, and there you can see there are a bunch of complex numbers, right? And we want to plot those things to see where they are. Correct? All right, so I'm going to do that. So I don't want to see that. So as a bxy will be the same thing, except it's coming from B, right? Then those are going to be the points, and fig image, not codomain, image will be list plot of that points, right? Correct? And I'm not going to show you the points. I'm going to hide that points by doing that, I think. And we still have those things, and I'm going to copy and paste. I'm going to do it by hand, not actually calculating anything. This is roughly how it looked like. No, I'm not doing this just to completely rely on the machine, just to convenient to do tedious thing quickly, but it's important for you to understand where they're going, right? Right. So we already know. So here is our, for example, target plane. Maybe U and V. We're hitting those numbers, and this is domain plane, right? And this is whole entire plane is called codomain. And this arrow is indicating the function e to the z. Is that right? E to the z. So we know this guy. What is this guy here? It's called 2i, right? Is that right? 2i. Where does that go into 2i? I think we already did it. E to the 2i. Let me write that down. E to the 2i. Modulus 1 unit circle argument 2 radian. 2 radian is, let's say, somewhere over here. Is that right? Somewhere over here. All right. This is this is radius 1. Is that all right? That's where that point A goes. Correct? Now, the something we haven't done yet is somewhere over here. I'm going to choose that point 1 over there. So what is that complex number? Is that 1 plus I? Are you able to see that? 1 plus 2i, right? 1 plus 2i is good? That's 1 plus 2i, right? So where does that go? Here's, I'm going to write that. E to the 1 plus 2i. Modulus? modulus is what? E, right? E to the x. Remember that real part contributes, not directly contributes to a modulus, but e to the first. All right? And argument is still easy, right? What's the argument? 2 radian, right? 2 radian before, 2 radian now. And you can imagine, wait a second, all this thing has a 2i part, right? Therefore, their argument is going to be always a 2 radian, right? Okay? So, how about the modulus this time? E to the first. This is where unit circle is, right? E to the first will be somewhere out here. Would that be fair? B is a B prime over there. Okay. So C will be over here. C, that point is a -1 plus 2i, correct? So I'm going to write that down here. E to the -1 plus 2i. Modulus 2 again. Modulus is different, but the argument is 2 radian. So where's the modulus? E to the -1, right? Which is 1 over e. Therefore, shrunk down to somewhere there. Would that be fair? C prime. Now, can you picture what's going to happen to all 60 dots? 60 dots is going to line up in that line in the second quadrant, right? This sensitive question is also important. How about the spacing of this one? You see the uniformly spaced 60 points, right? How are they going to be spaced? They're going to be dilated, right? Here they're closer, and there is a, we call it a stretch. If you look at it as not 60 points, it's a continuum of a line segment from -3 to the +3, you can see that somewhere it's a stretch and somewhere it's shrunk down. That kind of thing is called a transformation. This line is transformed under this function. Somewhere is a stretch and in that form. So you picture the image, right? So let's verify that by deleting that. And here it's not quite correct. So I'm going to fix that down there with the correct order. That's a 2 radian. You can see the spacing goes up and all in correct scale. Make sense? All right. So we're going to do a little bit of exercise together. Nothing part of your grade, but just enjoy this e to the z. So fundamental and important, right? So let's do that together a little bit. Now I'm showing the collection of points in the domain, right? All lined up at 1. And I want you to go ahead and try, just try 1.8. This is a real number. I definitely have a clear idea where is it going. Trying this number and that number will probably, just 3 number if you try, you have an idea how they look like, right? So why don't we spend maybe 2 or 3 minutes, all of you individually, try this one. I'll do that here myself too, and I'll show you the computer-generated image. So how was it? You managed to plot a couple points? So I looked at this 1, that goes to E, definitely. I looked at this point there, 1 plus I. Modulus is e to the first, still e. And the argument is now 1 radian. So I kind of circled it around that modulus before because it's the same thing. So it's over there in that point with 1 radian roughly. And the other point down there is a -1 radian, but real part 1, that still goes to the same modulus condition. So it's there going around like this. So does that give you a clear idea? What is all the points on this infinite vertical line it's going to go? How about the spacing? What do you think is going to be spaced around evenly around there, or somewhere stretched and somewhere not? Right, I think it's the angle contributing to increment of angle on here, exactly right. So I think it's going to be uniform. What about all this money, lots of points over there? Is it going to be crammed in or some different fashion? Crammed into this circle or not? If not, what could be the word? Just keep wrapping it again and again, right? If you reach the 2 pi I there, that's going to be 1 rotation. From that on, it's going to keep rotating again and again. So all this point is kind of repeating, right? Clearly not 1-to-1. Do you see that? Clear. Some points are going to same points, right? So clearly not 1-to-1. In complex function, you don't expect 1-to-1. It's all wrapped around and it behave like that. So let's go to there and let's see if our calculation is correct. Then you wrap around like this and up to the 3. But if you do more than 3, that the points will be appearing over here. Not exactly, because we're moving by 0.1 and this entire thing is irrational number and we're moving it by rational radian, so it'll never overlap. It just keeps spreading apart. Does that make sense? If it's overlap, it has to be entire rational multiple of 2 pi, but that's not how we're increasing. We're increasing by 0.1 radian, so it'll never overlap. But as a continuum, yes, it is wrap around that. Make sense? All right. So we're not going to spend more time on and how the other things are doing, but we'll just quickly guess what's going to happen if we do this without really doing work. Just think of this is our domain, right? K plus Ki. Does that make sense? K plus Ki. This is the line. What's going to happen to this image? Modulus is increasing or fixed? Look at these points here. Modulus is coming from x. Is x changing? X changing, right? Increasing. How about argument? Is argument changing? Argument is not changing in here, right? But that's not the argument we're looking for. Argument of the image, not the argument of z. Argument of e to the z, right? Argument of e to the z is a y portion in here. Y portion is also changing. So we're starting from 0. Where does 0 go? 0 goes to 1, right? And as we go from here, modulus is increasing and argument is also increasing, right? And so you start from 1 and think about what on earth is here. We're starting at 1, and as we go, the modulus is increasing and it's increasing like that. So what's a good term to describe this curve? You might have seen this in a parametric equation and things like that. All right, you can do that one at a time. It turns out, hey, that's there's something wrong. Oh, because we start from all the way in here. That's why. But we do hit that 1.1 in here. That's 1. We have other portions that's contributing to that, like that. All right. So what's happening to that point? It seems like going to e to the -1 or something, right? All right. So let me ask this now. You got used to this idea, and let me ask you this question. Not only these points. Let me re-summarize it here. This is entire xy plane domain. We're not looking at just collection of points on line. We're thinking about all the points here is going to UV plane under that function, right? Okay? We saw that this is not one-to-one. Can somebody explain why this was not one-to-one again? Right, it's a vertical line. It's just right next to it. If you go over there, vertical line, it repeats point over and over, right? It's not one-to-one. 2 points are going to the same thing. Functions, that's one thing we consider, one-to-one or not. What is the second property that usually comes? Injective is one-to-one. Surjective or onto property. If I choose an arbitrary point in here, will there be some domain point that hits that? That's onto property. Every point in this codomain is hit by that. So the question is this onto? So let me write down the picture. E to the z is simply e to the x plus times e to the cosine theta plus I sine theta. Is that right? All the numbers in here must be written in this form so that there is xy that's corresponding thing, right? I choose an arbitrary point. If I can write that point into this form, I know which x and y is going to be, right? So let me go ahead and fix that. This is supposed to be y. Is that right? Yeah. This is clearly in that that's modulus form. Whatever that has modulus in there, right? I can match that with e to the x. whatever that is has some argument in that. I can match that with y. Does it look like an onto function? It's not onto. You cannot match one modulus. You can match all the modulus except one modulus. Which modulus can you not get with this e to the x? E to the x can hit all the number except 0. Modulus can be 0, right? Modulus can be 0, but e to the x will never be 0, correct? Therefore, which complex number is missing under this map? The complex number with the modulus 0, which is that one right there. Under all that map is going to hit everything many, many times, infinitely many times, except that 0. That's the function. Okay? It's not onto. Okay, I'm back. I didn't know there was a space then there. All right. Let's see. Let's go back to the e to the I theta. And cosine theta plus I sine theta. Well, this clearly shows how this cosine and sine and e to the x are connected, right? But let's actually write it down. All right, how would you write this cosine theta, in terms of... Remember, the cosine theta is a real part. Remember? How do you isolate real part? Using conjugate, right? Using the conjugate. So if I write down cosine theta minus I sine theta, right? And if you add these two, you get rid of the imaginary part. If you subtract these two, you get rid of real part. So you isolated sine and cosine. That's the idea. So how do you write this one in the polar form? This is not quite in the polar form because of the negative sign in there, right? How would you write this one in the polar form? I can bring that negative inside the sign because sine is what function? Odd function, right? How about there's no negative in there? What are you going to do? We can just put the negative in there and it's going to be okay because cosine is even function, right? So this one is better known as e to the what? Theta parenthesis negative theta, I theta, right? So you can put it in this way. Make sense? Okay. So that has now a new name, e to the negative I theta. So how do you isolate cosine theta? Cosine theta is going to be sum of these two things, right? Then a sine part goes away, e to the I theta plus e to the negative I theta, right? If you add those two, sine part goes away. 2 copies of a cosine shows up. So what's cosine? Divided by 2. This must be familiar to you. This is something called some hyperbolic function, right? Cosine hyperbolic function, this is exactly. And the derivative of a cosine hyperbolic and sine hyperbolic behaves a lot like the derivative of cosine and sine, remember those? And the algebra even, the addition formula looks a lot similar. First time when I encountered it, I thought, this is real strange. How can something like this happen? I thought those addition and subtraction formula is really characteristic for sine and cosine. And that was a sure sign there's a connection, and this is explained why there is that similarity in there. Make sense? All right, who wants to go for sine theta then? Sine theta, we're going to do similar arithmetic to these two things, right? What do we do? Subtract. Second form, e to the I theta minus e to the negative I theta, right? Then you're going to have what function? 2i sine theta, right? So you divide both sides by 2i. Does that make sense? This is called sine theta. Now, if you have definition of e to the z, sine theta and cosine theta is described in this way. And yet the theta is a real number, right? And this gives us an idea. How should we define cosine of z? Do you know what I'm doing? What is this business called? There's a cosine theta where theta is a real number. Now I'm about to go to complex input. What is this business called? Analytic continuation. You have a real function in there. How can I go naturally without disrupting this existing world? How do I naturally sneak into that function that is extended, analytically continued? What would you do? Hey, that's a real number, that's the theta, and if I put z in there, it makes perfect sense, right? Because e to the z makes sense. So it is not e to the z. I is there already. You have to replace that theta with a z. If it's going to be okay, and this must be it. Let's see, e to the negative iz in there, divided by 2. So this is not a theorem, right? What is this called? Definition. We define cosine z is going to be like this. And I was saying, if e to the I theta is okay, this guy is going to be okay too. It's all relied on the question, is e to the I theta definition okay? Right? How about sine z? You get exactly the same thing. Make sure you don't lose that I because you only, hey, it has to be e to the z. I is supposed to be in that z. No. I is actually the coefficient multiplied to z. Alright? So that's a common thing that students lose. E to I. If you just replace that variable to real number, this right-hand side makes perfect sense. Therefore, we accepted this as a definition of cosine z. Alright? Okay. So now, we have e to the z, and cosine z and sine z, and there are connections between. This is not all three different. It's all combined into the same function under the complex numbers. That's what I was saying in the first class. These three functions becomes one function under the system of complex numbers. So here's a fun part. Solve e to cosine z equals 2. Cosine theta will never hit 2, right? Cosine is x-coordinate of the unit circle, correct? So x-coordinate of a unit circle will never exceed 1 or beyond negative 1. Must be in between 1 and negative 1. Now we extended this cosine to something else. Who knows what's happening, right? So let's look at this cosine z. See if we can solve it. Number one solution is not necessary. I'm just playing with that a little bit. I just want to feel what that negative theta is. Not x plus y. I'm just going to play with this. Let me see. Y. Let's try simple things. So what is the definition of cosine again? E to the I z, right? What is z here? Iy is what it is Iy, correct? Plus e to the negative I Iy. That's the definition. Is that right? You can see I disappears. It becomes a real number, right? That's good because we wanted to pull out a real number. Isn't that just a real number? E to the negative real number and e to the y real number, right? And we're hoping that this is going to hit what number? 2. You can solve that. Okay, how do you solve this equation? Maybe I'm going to call t to be e to the y. And do you see this nice equation? What's a good name for the first term in there? 1 over t, right? Reciprocal 1 over t. Plus, what about this one? T equals, divided by 1/2 equals 2. Do you think you can handle this equation? Yes, it's a quadratic equation if you multiply t both sides. And you can solve it, right? Hope t is going to be a real number, right? Because t is supposed to be a real number. So, it actually t exists. In the real number exists. Okay? But number 2 is that, well, why are we doing like this? We can just start always like this cosine z and just look at it e to the z and e to the iz and e to the negative iz divided by 2, and that's set equal to 2, right? That's all we want to do. So what is the substitution you have to make in here? W is going to be e to the iz, right? Then the other one is 1 over w, correct? So that one is like 1/2 times w plus 1 over w equals 2, right? Wait a second. Am I doing something wrong in here? Oh yeah, because the I is missing. And you're going to see this one turns out w is plus minus iy form. That makes no sense. But it should do it. This is w, and this one is a negative w because it makes sense for... yeah, since we have time, let me finish this one. All right. Ignore that. I'm going to finish this problem with this one. It's a more general method. So if I multiply 2 and w, I get w plus 1 over w equals 4. Is that right? And if I multiply w, I get w squared minus 4w plus 1, right? Equals 0. Am I missing something? All right, so what is w? Quadratic formula, right? 2, and that's plus 4 and plus minus 16 minus 4. That is right. So it's a 4 plus root 12, 2, and that's 2 plus minus root 3. That is right. Okay, 2 plus minus root 3. W is supposed to be a real number. 2 plus minus root 3. This is how you go rest upon. Right. W is supposed to be e to the iz. That's where the z is, right? And this is supposed to be 2 plus root 3, and or e to the iz being 2 minus root 3. Okay? Now we have to compare that, and it goes like this. We're going to solve e to the I. We're going to figure out in this part. Then you can make a connection to real part and imaginary part. So that's e to the negative y plus ix. Did I have this right? Because of that I, z is supposed to be x plus y form, and we want to figure out what that x plus y is, and it switches to that. This is 2 minus root 3, 2 plus root 3 first. And if this is a real number, would you believe that that is the modulus? Right? If it is negative number, you have to swap that. If it is a negative 5, then modulus is 5, right? And the argument is pi. If it is a positive number, that is the modulus. And what is the argument? 0. I theta 0 radian. Does that make sense? The real number, 2 plus root 3, in a polar form, if that real number is a positive, that modulus goes there. That's the length itself. And real number in the positive real axis, therefore argument is 0. Make sense? What if it is a negative number? What do? Change the positive number and put what angle? Pi. You see the pi is over there, negative number. Negative real number is in there, right? Okay, that's something we have to do. All right, so this is what? E to the... So let's match this one. Should have prepared this better, but almost done. If these two things are equal to each other, what is the solution? Modulus must be equal to each other, and argument be almost equal to each other. What is the word? Argument be coterminal, right? So what is the modulus of this one? Not x, right? What is the x real part in here? Negative y, right? So isn't the modulus e to the negative y? Correct? It's supposed to be what modulus on the right-hand side? 2 plus root 3. Is that right? Modulus to be equal to each other. How about angle? What is the argument in here? Left-hand side. X, right? But what about right-hand side? Argument is 0. But they're not equal. Up to 2k pi, right? Coterminal, so you have to write a 2k pi. So how many solutions are there? As long as this is true, these two things are equal to each other, right? So modulus had no choice. Y is going to be log of whatever. But what about this one, x? Infinitely many choices, right? Where are they? They're all in the vertical line. Remember, the infinitely many things go into one point. So you'll find many of them. All right, that'll give you y as a negative ln 2 plus root 3. If you solve this one using the logarithmic. And if you want to find one general solution on x is going to be 2k pi. So let's go back to the z. What is z? X part is a 2k pi plus negative I times ln 2 plus root 3. If you change that k part, that's going to be horizontal line, right? They all go to that. But that's the only one side. What is the other solution? E to the I x plus yi is equal to what? 2 minus root 3, right? And you proceed the same thing. Since I'm over time, I ended repetitive. All right? So you can solve it completely by entering polar form and matching the modulus and the argument being coterminal to each other. We have complete description of the solutions that. And there is a complex number that cosine of z equals 2. That's one thing I'd like to mention, right? Now you entered cosine can be anything now. All right, I'll see you next week.